Hi, I want to talk you through this following example of a motion problem. Now, first of all, you should ask yourself, how do I know that this is a motion problem? Well, if we read the problem carefully, it does talk about a train traveling at 40 miles per hour. It also talks about 8 hours here. So we have a rate, we have a time, and it talks about them traveling in the same direction. That's also very important. So one of the first things I want to take a look at is what's really happening in this example. Well, there's a rate, a time, and a distance that's going to be happening. And so what we're looking at is a problem that is rate times time equals distance. Now, frequently when we have this kind of a problem, we can take the information out of the problem and try to put it with these three letters into a table. And so you often will see a table associated with the problem. Now, two things are happening here. We have train A and we have train B. And those two I'm going to put right here on the side. So for each of these trains, I should be able to fill in the boxes that I've created here in the table. So we start by asking us, well, what are we actually looking for here? Well, if we look at the question that's being asked, that often gives us a pretty good idea. Now notice this question says, how long? Well, how long? What does that refer to? Well, it certainly seems like how long would answer a question of time. And so what I'm looking for is a time feature here. So let's identify a variable. Let's call that variable x. Well, what is x going to represent? Well, in this case, I want to know how long does it take for train B to catch up to train A. So I'm going to call train B's time is going to be my x. Okay, so let's go back to the table and fill that in. I don't know train B's time, so I'm going to call that x. Now let's look at the other information we have in the problem. Well, it says train A right here is traveling at 40 miles per hour. So that's a rate. So I'm going to put 40 in under the R for train A. Now what about train A's time? That's not given specifically in the problem, but remember that X was what we call train B's time, and we know that train B left 8 hours later. So that means train A, when it starts, now let's think about that. Train A is traveling in the same direction as train B is traveling in. But train B leaves 8 hours later. So how can I represent that? Well, B is not traveling for as long a time as train A is. So I'm going to call the time for train A. Train A will be traveling 8 more hours than train B. So I need to add that 8 in there to account for that time. That's how it relates to the x. Now, what other information do I have in the problem? Well, I also know that train B is traveling in the same direction at 60 miles per hour. So there's another rate. So that goes into this first column for train B. Now remember, I had said that rate times time is equal to distance. So anytime you have two columns filled in, you can fill in the third using that information. So if I want to know the distance that train A has traveled, I don't have an exact number, but it is 40 times x plus 8, because it's rate times time. The same with train B. It's going to be 60x, again, rate times time. Now what I'm interested in figuring out here again is how long does it take for train B to catch up to train A? Well, if train B catches up to train A, and I look at how far they've traveled, they have traveled the same distance. So that information tells me what I can do to solve the equation. In order to write an equation here, I know that the distance of train A has to equal the distance for train B. And so my equation is 40 times x plus 8 is equal to 60x. And I think once we get to this point, you can probably take it from there and solve this equation for x. Remember, when you find x, x represents the time that it took for train B to catch up to train A. And the last question would be, is that the answer to the problem? So I'll leave you with that.